last class period, I just barely started talking about stars in general. We finished talking about the sun. So we started by talking about how we know the distance to the sun. And what was the method we get for the best method for getting distance to the sun? There's more than one method, but what's the best one? Radio waves. Now, you said parallax. That's a good way to find nearby stars. So we went from there to the parallax. That was the next thing we talked about. So, what was that? Parallax is measuring how the angle changes. And so that's what we're going to pick up today, is talking about the parallax distance measurement. Why are we doing this? Because it's kind of important to our understanding to know that there is a reason for scientists to believe they have distance and to be able to evaluate how much faith you have in that method. You know, I think the radio method we have a lot of faith with. After all, we get tickets from that method, right? Cops use that method. Well, they're measuring Doppler shifts, which we're going to get to later. So we have even more reason to have faith in that, sadly. The parallax method is a method that we can readily understand. Like I said, if I'm over here, the angle from that bookcase to Eli is 9 degrees. And I walk over 1, 2, 3, 4 paces, and now the angle is more like 80 degrees. And so I can take the difference in angle and the distance I traveled, and using trigonometry, I can determine what that distance is. So I ended with this slide last class period. You know that, well, I'm just not going to go into the trigonometry here. It's not hard, you know, showing a full circle and breaking things up. But the simple relationship is the distance to an object is inversely proportional to the size of the apex angle there, the angle marked P, that's called the parallax angle. And if we use the baseline is 1 astronomical unit here, notice it says 1 astronomical unit, and measure that angle P, then we get a relationship, and the relationship is actually 206.265 astronomical units on the top. So that's 1 parsec. The only thing that's really important to know about this is that angle is measured in arc seconds. The name parsec means parallax arc seconds. I had to sit here and think for a minute. Parallax arc seconds. So it's using the parallax method based on how many arc seconds you have for your angle. So we should review what an arc second is. A degree is 1/360th of a circle. A minute is 1/60th of a degree, and a second is 1/60th of a minute. So an arc second is 1/3600th of a degree, and then you take that 360 and 360 times 3,600. An arc second is that much of a full circle. Why do we have this funny number here, the 206.265? Because the natural units for angles are radians. There are 2 pi radians in a circle, or 360 degrees. And so we have to go through the conversion factor to convert from the degree to the radian to get that number. So how is this useful? Let's go back in time. Well, okay, we can't go back in time, but you know what I mean. Back in the time of, let's say, Aristotle, people were thinking really great thoughts. We had people who had come up with the idea that the sun was the center of our system. Well, they thought the universe. And we had people who had calculated, not just determining the Earth as a ball, but had calculated very accurately the diameter of the Earth. They didn't accept, most of them did not accept that the sun was the center of, as they said, the universe, because they couldn't see the signs that should occur. They knew that if the Earth was going around the sun, that we should be viewing the stars from different vantage points, just like my example of walking across the front of the classroom. And so when we look out there at stars, we should see the angle shift as we're going around the sun. And they didn't observe that. They didn't observe any signs of parallax. So that, combined with the fact that they couldn't feel the Earth move, they knew that if they were in a chariot, they would feel it moving. They didn't feel that. They said, we have good lines of evidence to say that the Earth is not moving. The Earth is stationary. And so by and large, people rejected the idea of a heliocentric universe for those two reasons. So now I'm talking about parallax again. And what's different? Well, we now make observations with telescopes. And we have very precise measuring and mounts that can be very carefully adjusted. And using satellites orbiting the Earth, we now have thousands of stars that we actually can measure a parallax angle for. We can see IS. It's a different angle when we view compared to other stars to this star. And based on that, we can calculate the distances to these thousands of stars using the parallax method. So we had radio waves for the closest stars to get the distance, like the sun. And then we can use parallax for the next closer regions of stars. Things like Proxima Centauri, the closest star to us. Or Alpha Centauri, the closest star we can see with the eye to us. Just for reference again, those are about 4.3 light years away. Now this here is a parsec, distance based on an angle. A light year is a distance based on the speed of light. It's the distance light travels in a year. And the two numbers are only different by a factor of, 3.26? So they're pretty similar in size. The stars are not stationary. On my celestial sphere, the whole model says the stars are fixed on a globe. But that's just a model that makes it easy for us to visualize. It's not fact. So what do we know about stars? We know that stars vary in distance and in motion. Some stars are coming toward us, very, very few. Most stars are moving away from us and also going at random directions. So this picture here is illustrating what the Big Dipper looked like in the past, and I cut off the dates. What it looks like now and what it looks like in the future. It's not always going to look the same. Now we're talking very large time periods for these variations, but the stars are moving with respect to each other, and so it's going to change what it looks like over time. The stars are not stationary. But we don't see the stars move because the angle they move, if it's going the speed of light, we're still not going to see the star move because the angle that it makes over one night is going to be absolutely negligible, even if it's moving the speed of light. So we don't see this motion, but like every 10 years or so, astronomers will make up a new table. They call them the epochs of the positions of the stars. And they will shift ever so slightly because of their motion. So in 10 years, it's enough that you have to aim your telescope slightly different to be dead on. Oh, there was some terminology there I didn't mention. The star's motion toward or away from us is called the radial velocity. So a star coming toward us has a radial velocity toward us, away from us, radial velocity away. Proper motion is the term for the star's motion that's perpendicular to the radial direction. So it's the proper motion that's causing the distortion in those. Now, distance and brightness. The two are related. We had a quick equation previously saying that the brightness, that is how bright we see it, is inversely proportional to the separation squared because the light is spread out over a spherical shell and the area of the sphere is 4 pi radius squared. So if something is twice as far away from us, it's going to appear 1/4 as bright, 1/2 squared. So that's the relationship that relates brightness to distance. Now, luminosity is a different thing from brightness. Brightness is how much light we're receiving from it per unit. Luminosity is how much total light it gives off. So luminosity, it doesn't matter where you are in the universe, a star's luminosity is going to be the same because that's how much light it gives off. But it does matter how close you are for the brightness. So luminosity is an absolute measurement, same everywhere, whereas brightness is a relative measurement. And since I just finished talking about the brightness drops off with 1/distance squared, then we should have a nice simple mathematical relationship. Brightness is luminosity divided by 4 pi distance squared. Remember, area of the sphere, 4 pi radius squared. That's where the 4 pi distance squared comes from. So it's a pretty simple relationship, but now we have something that can give us a calculation for distances. I can take that equation, I can solve it for distance. I'm a bit of a mathematician myself, as Nathan says when he does these kind of calculations. I can take this and multiply both sides by d squared, divide both sides by b, and I get the equation that says distance squared is equal to luminosity over 4 pi brightness. So if I square root both sides, I have an equation for the distance as a function of that ratio of luminosity and brightness. Now, any reasonable person says, great, but what do we see here on Earth? We see the brightness. We don't see the luminosity. So how is that useful? That seemed like a reasonable comment. Well, for certain types of objects, we can determine the luminosity. In fact, it'll turn out pretty soon, you'll see we can determine the luminosity for virtually any object. But there are certain objects that have the same luminosity anytime they occur. For instance, when you have a nova. A nova is when you have a white dwarf that has gathered enough mass on its surface to suddenly have combustion on its surface. Those are pretty repeatable. Even more repeatable is, was it type 2A supernova? I'd have to go back and review which type. But the type of supernova that occurs when a white dwarf collapses. It always occurs with the same mass, the same composition, so it's always going to be the same brightness. Thus, if you observe one and you measure, I said it's going to be the same brightness, what should I have said? Luminosity, always going to be the same luminosity. So if you observe one of those and you measure its brightness, then you can use this relationship to immediately determine the distance. Okay, now I'm going to hit one thing that I've mentioned before, that interstellar reddening. There is a certain amount of light lost with distance traveled. So when astronomers use this, they're a little more sophisticated than just taking that equation alone, because they know you're also going to have some light that gets scattered away as it travels through space. So look, that equation should look familiar, right? Because we just derived it. The distance relationship with the luminosity and the brightness. Standard candle is the name we give to objects that have a brightness that we can always determine easily. So, like I said, certain supernovae are standard candles. Variable stars we'll learn about are another standard candle. There's certain things we can use. Now, a new system, and this is the hardest math in the entire class. So if this math is easy to you, yay, you're not going to have any hard math for this class. If the math is hard for you, well, you know it's not going to get any worse. So if we go back to, what was it? Oh, I think it was Aristarchus, but I could be wrong. A scientist decided to name the magnitudes of the stars. And the brightest stars were first magnitude stars. And then the ones that were a little dimmer were second magnitude stars. little dimmer still third, and you get down to the faintest ones that you could see with the eye would be like a 6th magnitude star. So somebody just came up with this idea. It's not mathematically based. But then astronomers took that idea and they folded it into a mathematical idea. So first thing to note is which ones were brightest. What magnitude was the brightest? 1 was the brightest. And what was dimmest? 6. Anything that we can't see with the naked eye, if we're going to follow that scale, where is it going to fall? Yeah, it's going to be a bigger number than 6 if we can't see it there. So the fainter it is, the bigger the magnitude. Well, what if there's something that's really, really bright? Something that's brighter than a 1st magnitude star? What's that going to become? That's exactly right, 0 or negative. So stars with a negative magnitude are brighter than stars with positive magnitude. Right? That just comes from taking that original thing and extrapolating it in both directions. So how did astronomers come up with a numerical version of this? They start by saying, okay, measuring the brightness, there was roughly a factor of 100 times brighter for magnitude 1 compared to magnitude 6. And so they said, okay, we're just going to make that our rule. If the difference in magnitudes is 5, 6 minus 1 turns out to be 5, not 100, then that is going to mean that it's 100 times brighter. And so we have an equation, not here apparently. I'm going to come back to this. We have an equation that says the ratio of the brightnesses is equal to 100 raised to the difference in the magnitudes over 5. Why the over 5? So that if you have a difference in 5, then 100 raised to the 1 is 100. And so that equation in the box is a mathematical equation to go with the relationship that we just described. And so we have an equation we can use. Now notice 100 raised to the 1/5 power is 2.512. And so the continuation of this equation here is just taking 100 raised to the m2 minus m1 over 5 is equal to 100 raised to the 1/5, all raised to the m2 minus m1 equals 2.512 raised to the m2 minus m1. So that's how the second part of the equation goes. Now, what if we want to actually solve for the lowercase m's? Lowercase m is used for the magnitude and in the way I've been describing it. Lowercase m is called the relative magnitude. Relative magnitude is measuring what we see on Earth for the brightness of the star. So if I want to solve that for m, I have to find a way of getting m out of the exponent. And this is where I said that the most significant math of the entire class is. To get the m out of the exponent, you have to use a logarithm. And so if we take that equation that's in red, and we do the log of both sides, and so we're doing a log base 10 here. So we do log base 10 of brightness 1 over brightness 2 is equal to log base 10 of 100 to the m2 minus m1 over 5. And that's equal to rule of logarithms that you may or may not know. Bring down the exponent m2 minus m1 That's one way of writing it. And so that is This number here, of course, is just a number. Log base 10 of 100 to the 1/5 would be 1/5 of log base 10 of 100. Log base 10 of 100 is 2, so it'd be 2 over 5. 2 over 5? For some reason there I have 5 over 2. I think I flipped I flipped something in my calculation and didn't show it because it should have been 2 over 5, not 5 over 2. Well, I'm not going to sit here and try to figure out where I flipped. But this equation here relates the brightness with the magnitudes. So you can quickly say, okay, if star 1 has a brightness that is 100 times star 2, then I would have 100 over, 100, B2 over B2 is 100. Log base 10 of 100 is 2. 2 times 2.5 is 5. And I'd have a difference of 5. Now, I told you I was going to go back. And so I will go back now. The relative magnitude is the magnitude that we see on Earth. The absolute magnitude is a different idea that's telling us about the luminosity. The relative magnitude tells us about the brightness, how bright a star is on Earth. The absolute magnitude tells us about the luminosity, how much light it gives off. And so the absolute magnitude is simply the calculation of what the relative magnitude would be from a distance of 10 parsecs away. So what we're setting for the absolute magnitude is, if you're 10 parsecs away from the star, what will its apparent magnitude be? That's the absolute magnitude. And so for the absolute magnitude, we can use the brightness relationship to shift positions. So that's what is going on with this equation here. Capital M is the absolute magnitude. Lowercase m is the relative magnitude. And the difference between the absolute magnitude and the relative magnitude has to do with how far you are from the star. So we use the relationship for brightness that we saw previously. Remember, we had brightness is equal to luminosity. Oh, let me just erase all this stuff instead of repeating the equation that's in black. The brightness is equal to luminosity over 4 pi d squared. And so putting that equation in for the brightness, we can solve this equation. So brightness 1 over brightness 2 is going to be proportional to the distance over 10 parsecs. And we get this relationship that allows us to calculate the actual distance a star is away if we know its absolute magnitude and we measure its apparent magnitude. So where the rubber meets the road on this, what we need to know, be able to operate with, is first of all, knowing that the apparent magnitude is measuring how bright a star is, that is, how much light we receive from it on Earth. And that the apparent magnitude difference has to do with the ratio of the brightnesses, and we can calculate, and you should be able to calculate, you should be able to use this equation either in this form or in this form. It's the same equation, just 2 different forms, to relate brightness with magnitude, the apparent magnitude. This table here is to just give you a feel. If the difference between the magnitudes is 4, then the ratio of brightnesses is 2.512 raised to the 4th power, 39.8 to 1. And so you can get a feel for the numbers, but you still should be able to do the calculations. Now, look at this once again. If I have 2 stars and the difference between them is 4, how am I going to know which one's the brighter one? See, I know M1 is 3 and M2 is 7. How do I know which one's brighter? You want the smaller number is always the brighter one. So when you have these, keep that in mind. And notice it's M2 minus M1 is 2.5 log of B1 over B2. So the one with the bigger magnitude, if this is a positive number, it's going to be the one that's in the denominator here. All right. Next thing is you should be able to calculate the distance something is away if you know its absolute magnitude and its apparent magnitude. So notice it's 10 parsecs times 10 raised to the m minus capital M over 5. We can bring this 10 in here and just raise the exponent by 1. So this 10 here disappears because we added a 5 over 5. 5 over 5 is 1 to the exponent. So these two equations are exactly the same in meaning. This one here is generally going to be easier to calculate because it's just one less step. So be able to determine the distance if you know the absolute versus apparent. Be able to determine the difference in brightness if you know the two apparents. This is very useful for astronomers because if you know one reference star, like let's say you know where Vega is, and you look up and you know what the apparent visual magnitude of Vega is. Does anybody know the apparent visual magnitude of Vega? Let's look it up. I don't have my phone here because I came that prepared. Somebody look up, what is the apparent visual magnitude of Vega?
It says 0.03.
0.03. Is that bright or dim?
Bright.
Bright, right? That's brighter than a 1. So Vega has, you said 0.13?
0.03.
0.03. Okay, so it's very close to 0. Now let's do something fun. What is the apparent visual magnitude of the sun? First of all, before she looks it up, I trust Juliet so much. Is it going to be a big number or a small number?
Small.
Small. Positive or negative?
Positive.
Okay, look it up.
Negative 26.74.
Negative 26 point what?
74.
Okay. I'm going with that's a big negative number. It's really, really bright, right? Of course it's really bright. We need that in life. We need its energy. So, how much brighter is the sun than Vega? How much? A lot. Okay, Juliet already answered it. But we can actually calculate that. We can calculate the ratio of the brightnesses. So the ratio of the brightnesses is going to be 2.512 times the difference in those magnitudes. So that means I'm going to have 2.512 raised to the nice job. 2.512 raised to the 26.77. That is how much brighter the sun is. So not my calculator. That's my excuse, and I'm sticking with it. There it is. Raised to the 26.77. That is 51 billion times. The sun is 51 billion times brighter than Vega. Now remember, that was brighter. That's not how much more luminous. In fact, which one do you suppose is more luminous? Probably Vega. How can we determine which one's more luminous? Do what?
Math.
Math. Wow, she's good, that girl. That woman. I don't know. For some reason, boy is not a problem, but girl is. I haven't figured it out, but I don't want to cause problems. Is that right, boys? You know, boys typically don't care, and I think it's because, well, it's a male-dominant society, so don't care because it's not used against you, right? That's what I think. Okay, here's how we can answer. And I'm once again turning to Juliet. She's my numbers person today. If we look at the absolute magnitudes, that will tell us how they would compare if we were 10 parsecs away from each. So what are the absolute magnitudes for those two? I know it is going to take you a moment.
On the sun, it's 4.83. And then for Vega, it says 0.03.
The absolute?
Yeah. Wait. No, 0.582. Sorry.
And so we look at that, and you can right away say which one's brighter. Or not brighter, excuse me. Which one is more luminous? It's going to be Vega because 0.0582 is a much smaller number than 4.83. In fact, we can determine now how the luminosities are going to vary by doing, once again, this relationship here. We'll just change it from lowercase m to capital M because we're the same distance away still. And we can just say, I've run out of space, and I have to write all over everything. But so this here was the brightness of the sun divided by the brightness of Vega. Now I'll put the luminosity of the sun, divide that by the luminosity of Vega, is equal to 2.512 raised to the minus, and that would be 4.2. Okay. 83 minus 22, 8. Two minus 8 is... Hopefully I did that right.
I mean, if you didn't, I don't think anybody of us is going to double check you.
You should be. You should be all over that. If you can find a teacher making a mistake, you should point it out. Lord it over him. Okay, 0.0200. That's actually very close to, I know it's not a difference of 5, but it's very close to a difference of 1/5. That is, the sun is about 1/5 as luminous as Vega. We're not that bright or that luminous of a star, our sun. I say we don't live on the sun, but it's our sun. Final thing we could do with these numbers, if space were to be no problem, we can determine how far away, for instance, Vega is or the sun is from these numbers. We're going to get a ludicrously small number if we do the sun, right? Because we're much closer than a parsec. So let's just do it with Vega. I'm going to at least change color so you can kind of figure out what's this calculation. The distance to Vega is going to be 10 times its apparent visual magnitude of 0.03 minus its absolute visual magnitude of 0.5, that's an 8, 582 plus 5 all over 5. Thank you. And so if we do that calculation real quick, 0.03 minus 0.582. I should have done this before instead of doing everything in my head. Plus 5 divided by 5 And that's 10 to the 0.89 parsecs. You could leave the answer like that. That is a legitimate math number. 10 to the 0.89 is going to be somewhat less than 10, but bigger than 1. And so I'm going to put that in the calculator just to get us a number. I'll put voltage 8896 based on what we have. And we have 7.76 parsecs away. So there we have a calculation for how far away Vega is from us. See how these equations can be worked? Like I said, this is the hardest math we're going to have all semester. So if that's easy for you, excellent. If it's not, well, you know it's not going to get any harder. Any questions before I move on? Then move on I shall. A question to make sure you understood at least some of all of these words that have been tumbling out of my mouth. So we just have a question. Star A has an apparent magnitude of 5, while star B has an apparent magnitude of 1. Which statement is true? Let me start with some guided questions. What can you determine from apparent visual magnitudes? You can determine brightnesses. So we'll cross out the luminosities. What would we need if we were going to do the luminosities? That actually does work, but not in the context of today's lecture. Okay, we need the absolute. Now, you might have noticed I said visual magnitude and my slide says magnitude. There is a modest difference. The visual magnitude is only measuring the brightness in the visible wavelength range, whereas if you just say magnitude, it's the entire spectrum. So there is a difference in them. It's often ignored by people at this level. Okay, brightness. What do we need to determine brightness? We need the appearance. Hey, that's what we have. Should be one of those two then. What would we need to determine the distance? You need both the absolute and apparent magnitudes for the same star to determine its distance. And then if you had that for both stars, then you'd be able to determine which one's closer. So that's not it. Need more information is not it, because we were able to identify, yes, we can determine which is brighter. And so now that we've gotten that far, how do we know which one's brighter? We don't need a calculator for this. The one with the smaller apparent magnitude, so B is brighter. How much times brighter? We need a calculator for that. What's the key for determining how many times brighter it is? It's the difference between the apparent magnitudes. This has a difference of 4. The difference of 4, I think, was 39.1 times brighter. Just come back here and we can look. Oh, 39.81 times brighter. So for that example, we had star B was 39.81 times brighter than star A. All of those pieces make sense? Okay. Changing things up again. a lot of important things coming out all together. Now we're going to talk about the specifics of determining the temperature of a star. I've talked about this before. I think I've given you pretty much everything you need. Do you remember how we can determine two different ways we can determine the temperature of a star? What? Okay, the color. The color is one of the two ways. We use Wien's law, or if you're American, I suppose you probably say Wien's law. And you know, we're probably all Americans here. Well, we're not. Many of us are, but you're a citizen of another country, right? Clayton, are you a citizen of the U.S. or?
Yeah, both.
You're dual.
Yeah, I know.
And you said you're not American. You were very adamant about that. I think it'd be cool to be a dual citizen, but yeah, nobody offered me that. So one way is using Wien's law, which is to look at the wavelength that has the strongest emission and calculate from that. What they actually do is they look at a couple different colors and take the relative strengths of those colors to do it. But it's the same idea. The other one is looking at the stellar spectra. Spectra, did I say that right? Look at the absorption lines in the spectrum of a star. You might have recalled the first slide from today's lecture had a bunch of pretty rainbows on it. That was looking at the stellar spectra, and I'm going to have it coming up here in just a moment. So here's the Wien's law equation. Temperature is 2.9 million kelvins times nanometers divided by the peak wavelength. So you get your spectrometer, the thing that breaks the light up into the different individual colors, determine what color is the brightest, put the wavelength in there, and that gives you the temperature. It's a good method, but it's not as accurate as the other method, so it's not the predominant one. Remember, hotter stars look blue, cooler stars look red. We've gone through that before. I have here a picture of the spectra from the other method, but I didn't talk about the other method yet. I will. It's on the next slide after. Actually, no, it's 2 slides after this. But I've got to go through Annie Jump Canyon's thing here before I move on. So around 1901, she came up with a way of labeling stars by their temperature. So we're going to talk about their spectral classes. And spectral class, color class, is telling you how hot it is. Right? So if it's blue in color, it's the spectral class of the hottest ones. If it's red in color, it's going to be the spectral class of the coolest ones. And so what she came up with this system, and I don't remember what any of these letters stand for, O, B, A, F, G, K, M, and then later on was added LT. So I have 2 mnemonics up there, one that I have perfectly memorized. Oh, be a fine gal, or guy, kiss me, and then with the added LT, like this. That's kind of easy to remember. It just gives you the order from hottest to coldest for the spectral classes. The other one, only bad astronomers forget generally known mnemonics like this. That's an extra tricky mnemonic because you have mnemonic which starts with an M, but it sounds like it starts with an N. That's probably not the one to memorize. You should have this memorized. For the exam, oh my goodness, I was going to give you a quiz today. I sat down to write the quiz last night, and well, guess what I didn't do? Give you the quiz. You're ready to be on Thursday or Wednesday. Yeah, you're ready on Thursday. Oh, class. You'll need to have this memorized. So since I didn't give you a quiz today, have it memorized by Wednesday so it can show up in a quiz and you'd be ready.
With the acronym?
Hmm?
Like the OB?
Yes. The order from hottest to coldest. Oh, be a fine gal, kiss me like this. Or okay. These over here are showing you what the spectra look like when you just look at the colors. Turn off the lights just to make it a little bit brighter. well, the contrast a little better. These are what the spectra look like, and those are not very good for analytical purposes. But this here is showing the intensity at different wavelengths. That's really useful. Now, one thing you notice here is, where is exactly the peak? This isn't a nice, smooth black body curve. And so that's a failing of the Wien's law method, identifying the peak wavelength, because you can't really see the peak wavelength. It's not smooth. But all of these little jags are telling you about the absorption lines. And so getting the information about the absorption lines allows you to precisely determine the temperatures. And you can see this here, it has, its peak is going to be over here in the long wavelengths. Is that hot or cold? Other way. Long wavelengths are cold. Short wavelengths are hot. So this one here is hot. This one here is cold. And if you look, you see that this one here has much brighter red than blue. That one has much brighter blue than red. Now, to be fair, you're going to get more of all colors with a hot star if you're the same distance away. But these are all adjusted so you can see the entire spectrum. And so it makes it look like there's less red in the hot star than there is in the cool star. That's not true. It's just adjusting for relative brightness. There's, relatively speaking, much less red than blue in that. Okay, so, another slide in between. The O's are the hottest stars, then the B's. And so those are the bright giants and have temperatures in the ballpark of 30,000 kelvins. What's our sun surface temperature? Ballpark? 5,800 kelvins. So way cooler than an O star. But on the other hand, an M star is going to be down around 3,000 kelvins. So we're almost twice the temperature of an M star, but only, 1/5 the temperature of an O star. Here is the picture that we had on the opening slide. And you can see things like absorption lines. I'm going to change to yellow. Okay, I marked out a few absorption lines. I'm going to erase my marks. But what you should notice is that in the center of each of those things that I marked, you have the greatest absorption. And so by looking at those absorption peaks and measuring the relative strengths of the absorption peaks, that gives you a very precise measurement of the temperature of the star. Now, the ones on bottom are a little confusing. Over on the left-hand side, we have the spectral classes. We have an O 6.5. Because O represents a fairly large range of temperatures, scientists subdivide not just O, but all of the spectral classes into 0 through 10. So 0 is the hottest, 9, actually I said through 10, 9. 9 is the coolest. So a B0 is hotter than a B6. And so you can see you go down the B0, well, O6.5, B0, B6, A1, A5, F0, F5, G0, G5. The sun is a G2. So the sun is somewhere around there in temperature. Then we come on down to the bottom of the M's, and then we have one that says F for metal poor. Here's something to boggle the mind. When I say metal, what comes to your mind? Steel. It's a very common thing, right? Because iron is the most common of our metals. To astronomers, metals are anything not named hydrogen and helium. So a metal poor star is a star that doesn't have much besides hydrogen and helium in it. If it doesn't have much besides hydrogen and helium, it doesn't have much absorption out there because it only has hydrogen and helium absorption lines and nothing else. How would that occur? It would occur if this is an original old school gangster star. If this is a star that has not had a star die in its vicinity and then formed out of the ashes of a previous star. That's what a metal poor star is. So metal pool stars are actually really interesting because they, as far as astronomers understand them, would represent what the gases were like before the first stars. So that's why this one here does not look at all like F4. Come up here to F4 and you see it has strong absorption there. It has some absorption, but it doesn't look like this. See those absorptions there? Virtually nothing, because it's poor metals. So why do we have that down there? To illustrate some of the weaknesses as well. And then we have a couple more. Moving on, this will be our, oh shoot, I'm out of time. Well, this was going to be my last slide. This tells you which elements tell you about the temperature. So that's how astronomers devise the temperature, by looking at how strong the different lines are. Have to stop. Have a great Sunday. I'll see you for lab tomorrow. I think it'll be clear again.
Sunday? Let's go.